Good morning. Welcome to our 18th annual Michael M. Abbott Award Lecture. I should note that we have a distinguished guest, Mary Abbott, Mike Abbott's wife. So it's very nice to see you and have you here to join us. It kind of blows us away that we're already on the 18th annual lecture that started the year Mike Abbott died in 2006. We really have two goals behind these series of lectures. So one is to honor the accomplishments of Professor Mike Abbott. The other is to honor the accomplishments of a distinguished colleague in the field of chemical engineering. And so today we're honoring Randall Snurr from Northwestern University. But first, I'm going to give you a little bit of background on Professor Abbott. Okay, so you can see the many distinguished honorees that we've had in the past. We were lucky that Jefferson Tester was able to speak the year that Mike died, so he was able to see the first lecture in his series. But you go through this list, it's obviously amazing number of distinguished colleagues that we have had honored by this award over the years. So to give you a little bit of background, so Mike Abbott was born in Niagara Falls. I still love this cartoon because this is a classic haircut, kind of the Dutch boy haircut that Mike often had. So he was born in 1938, and in 1956, he entered RPI as an undergraduate student. The other thing to note about that is also in 1956, Professor Hank Van Ness came from Purdue University to RPI to start his RPI career. And so from then on, they were like lifelong colleagues, but I'll kind of take you through the steps of that process. And so my first question this is only our new graduate students are allowed to answer this question. So after Professor Abbott entered in 1956, he actually took his first chemical engineering thermodynamics course. So does anybody want to guess what his grade was in that course?
Of course, A. Right?
So that would be your instinct, right? Brilliant man, co-authored books and everything else. So instead, it's a C. Okay. Now you could argue that that's the equivalent of an A- now or a bust, something like that. But that was one thing I loved about Mike is students would come in and they would talk about, oh, I'm struggling in this course. I don't understand what's going on. And he'd say, well, I made a C when I took thermodynamics. And you're like, wow, kind of blown away by that. But he was always very amazing in that characteristic. So here is his application for graduate study after he finished his BS in chemical engineering at RPI. The other thing students, at least the US students, may be surprised is that we used to have a foreign language requirement for the PhD. So Professor Abbott used French as his foreign language requirement. He finished his PhD working with Professor Hank Van Ness. Second Bureau coefficients of some organic vapors and vapor mixtures was the title of his thesis. If you go outside the building, you'll see a memorial plaque that we have that honors Professor Abbott. But during graduate school, he married Mary Abbott. And so we say that they formed a lifelong thermodynamically stable covalent bond through that marriage. And this is the plaque. Then if you ever just want to pause and be a day and go out and sit outside at that bench. So after Professor Abbott graduated with his PhD, he went to Esso, which became Exxon Mobil later on, worked there from 1965 to 1969. In 1969, he returned to RPI, eventually becoming Professor Emeritus in 2002. He still remained active and he really kept, I really devote a lot of what I learned about education is due to Professor Abbott and his mentorship. And so I think a lot of us went through, really learned a lot from him at that time. Unfortunately, in 2006, he died of pancreatic cancer, but we honor him because of his scholarship. So many journal articles, books, book chapters. We'll see a few of those in just a moment. His teaching an incredible role in not only helping develop the chemical engineering curriculum, but the general engineering curriculum through these ENGR courses, both undergraduate level and graduate level, and then a lot of service to the department and to the university, advising students, mentoring faculty, serving as associate head of our department for many years. And basically, he had an open door policy. So I'm not certain he even knew about office hours. They were essentially 8 to 5. So if his door is open, you were there, you were welcome to come ask questions. So here are some of the many textbooks he was involved with. The Smith and Van Ness, which became Smith, Van Ness, and Abbott. And finally, on the 9th edition, there's actually a 4th author now from UBuffalo, Swihart. You can see it was translated into many different languages, including Greek. And so I always like to picture a Greek student taking this material and saying, "Oh, this is all English to me." And so Sham's outline series and a lot of other publications. The other thing is, if you want good teaching evaluations, don't co-teach a course with Professor Abbott. I'm pretty certain the times I co-taught design with Professor, they weren't listing me as the best professor they ever had, but constantly, no matter what course Mike was teaching, he got these types of evaluations, including Abbott Rocks. He received a lot of different awards during his career, from the Western Electric Fund Award, Faculty Alumni, Rensselaer Distinguished Teaching Fellow, Rensselaer Alumni Association, a Concord Award from the ASEE, Daring Counseling Award, Trustees Outstanding Teacher Award. But again, here's Mike. And this looks like a mess, but that's actually not Mike Abbott. I mean, he was very precise. He knew where everything was on his desk at any point in time. And then this is when we also have another seminar series, the Van Ness Lectures. And so this happens to be the first time we gave the Van Ness lecture, and that was Professor Van Ness and Joe Mock-Smith, the co-authors on Smith, Van Ness, and Abbott. Okay, so now I'll pause and give a little bit of background on Professor Snurr. And so he did his undergrad at Penn, Ph.D. at Berkeley, postdoc at University of Leipzig, and then went to Northwestern University, where he rose through the ranks and is now the John G. Searle Professor. But we always do due diligence. We want to make certain that somebody really did get their PhD. So I confirmed, I found the PhD thesis from Berkeley, read through it, very nice job. I learned about in the process. So these are selected awards. So Professor Snurr has won a lot of different awards, ranging from the Fellow of the International Adsorption Society, IChemE, Saxon Academy of Sciences, the Keeley Award from Chicago Local Section, Major Win Fellow of the American Association for the Advancement of Science, and Institute Award for Gas Technology, and Career Award, and several others. The other thing we like to do is, of course, in chemical engineering, it actually is only kind of 1 degree of separation. You go to AICHE meeting and you've got a direct connection with almost everybody at that meeting. But I like to go through and see what our direct connections are here with Professor Snurr. So one of them I mentioned, he was the IAAAS Fellow. And so he was honored for advancing the application of nanoporous metal organic frameworks. You can read it yourself. It turns out that we also have 4 faculty that were fellows, including a young dean that you may recognize from this. You look like that's just a couple of days ago, it seems. We also have another connection through Northwestern University. I mean, that's a pretty pathetic photo. But Professor Emeritus Pete Wayner did his PhD at Northwestern University. Professor Zah did her PhD in material science and engineering at Northwestern. And then I did a sabbatical at Northwestern University in 1996. During that time, I was writing my first textbook on process dynamics. I was actually writing it often at a coffee shop in Chicago and would go to these Cubs games. So here, if you would go to a Cubs game, you would get $5 seats if it was like April or September. Right? So this is a big splurge, like $15 for a club box. It's just a few rows up from my first base line, just amazing. $15 wouldn't buy you a beer at a ball game anymore. Okay, so one thing when I was at Northwestern writing this textbook on process dynamics, I'd really gotten enamored by James Gleick's book on chaos from 1993. So I really got into nonlinear dynamics, and I was introducing it into my classes at that time. And so you actually recognize this type of behavior from the lecture last week, known as hysteresis. So in my textbook, I'm showing, an independent variable here and versus some what we call like a bifurcation parameter, where at certain values, the bifurcation parameter, you've got a monotonic response. Then all of a sudden you go through a hysteresis bifurcation. And finally, when you get to this value, you get so-called hysteresis behavior, or if you start on this side, you have the sudden jump up here, start up here, it's a sudden jump down below. And of course, since I at least read the title and abstract of your talk, I actually dug up one of your papers. And so you have this to look forward to. I think you may have this slide today, or so you'll have something similar, I'm assuming, today's talk. But really what Professor Snurr is going to show is this is kind of the onset of a hysteresis bifurcation. And then down here, he's changed this parameter, so he'll let us know what this parameter is that he's talking about. And you can see that classic hysteresis, depending on whether you're going through adsorption or desorption stages. Okay, so I think that's enough about me. Although one other thing I already noted was that Professor Van Ness, he was always adamant about using Gibbs energy instead of free energy. But you're welcome to use whatever is most appropriate for your talk. Yes.
The Nobel prizes in chemistry were just announced this morning, and we could not have a better speaker today than Professor Snurr to talk about.
Wow.
It's given to metal organic frameworks. Yeah.
Excellent. Okay, fantastic. Well, join me in welcoming Professor Snurr to the podium.
Thank you. Well, thanks, Wayne, for the lovely introduction, and thank you to the department for this invitation. It's really an honor, and I'm very thrilled to be here. So yeah, this is my title, which Wayne mentioned, and I did my homework. I did a reading about like Abbott, and I never had the pleasure of meeting him. So like many of you, I know him mainly through his textbooks, and in particular, the classic undergraduate book. Pictures online are quite scarce, but I found that one. And I found a bio and also an obituary, and I was reading through it, and I noticed a number of parallels in our lives. So he grew up on a fruit farm near Youngstown, New York. I didn't grow up on a farm, but I grew up in a small town near a lot of orchards in Pennsylvania. Professor Abbott played the French horn. I played the trumpet. His father was a teacher. My father was a teacher. And he taught thermodynamics, and I have taught and continue to teach thermodynamics. So in deciding what to talk about, I sort of took advantage of the fact that, he was in the area of thermodynamics, and so I wasn't shy about putting thermodynamics in my title, and the talk will be somewhat fundamental. So this is an overview of what my group does. My group is generally interested in developing new materials, primarily adsorbents for separations, some work on catalysis, and we've kind of dabbled in membranes and nanoparticles. And we're a computational group, so we're taking advantage of the fact that computers are getting exponentially faster, and so we can model these very complicated materials at the molecular level and predict macroscopic properties that are useful to us as engineers. And so we're trying to take these tools and develop solutions for problems related to sustainability, energy, and national defense. And you can read here some of the things we've worked on over the years. So my whole group is really focused on nanoporous materials. And you might ask, okay, why such a focus? I think as chemical engineers, it's probably clear, but one way to think about this is porous materials with well-controlled structures at the nanoscale can recognize and discriminate between different molecules. And so we can exploit that in separations. So for example, you can separate air into oxygen and nitrogen. currently very focused on capturing CO2. In catalysis, you might think about these pores pushing a reaction down one pathway that you want versus another pathway you don't want. Sensing, or you can think about storing molecules in these little cavities. And so nanoporous materials have been around for a long time. Carbons are thousands of years old. Zeolites have been used industrially since the 1960s. And what I'm going to talk about are these metal organic frameworks, or MOFs, which are a more recent class of porous materials. They are porous crystalline materials, and they're made in a really interesting way from metal nodes that are connected by these organic linker molecules. Some of them have enormous internal surface areas, and by choosing different nodes and linkers, you can really think about tuning these for different applications. So, you could think about making the linker longer or shorter, or putting different chemical functionality into the linker that might bind particular molecules you're interested in. And I show you here just two MOFs from my collaborators, Joe Hupp and Omar Farha. They're in the chemistry department at Northwestern, and we work together very closely. And as Shekhar mentioned, if you looked at the news this morning, the Nobel Prize was awarded this morning for MOFs. So Susumu Kitagawa, Richard Robeson, and Omar Yagi for really creating this new field. And I was at the EuroMOF conference 2 weeks ago. There were almost 700 people there. So it's a huge, really actively growing field. This is a picture of some MOFs. These are typically micron-sized crystals, but you can form them into larger particles for industrial applications. And as I sort of hinted at, there's this enormous diversity of different organic linkers, different types of metals that have different connectivities. And so there's this enormous number of structures. And one of the key things that my group thinks about is this question of material selection or discovery or design. If we have some application in mind, say we want to capture CO2 from power plants, and that there are tens of thousands of existing MOFs and millions that we could dream up, how do we rapidly find good candidates? So what I'm going to talk about today is largely motivated by thinking about adsorption of water. So, adsorption of water is important in a variety of applications. Something like water harvesting, we want to absorb water. Something like CO2 capture, we might want to avoid capturing water as a competing molecule. So that's kind of the generic motivation. And adsorption of water in nanoporous materials often displays hysteresis, as Wayne mentioned. And in the last part of the talk, I'll also mention that it can be very sensitive to just local flexibility in these materials. So this is the outline. I'm going to start by talking about adsorption hysteresis, and I'm not going to talk about water. I'll talk about a simpler model system, and then I'll shift and talk about simulations of adsorption of water. Okay, so just to make sure we're all on the same page, Wayne already introduced this, but what I mean by adsorption hysteresis is if you're measuring an adsorption isotherm, so the amount absorbed in the material as a function of pressure at constant temperature, sometimes you see a curve on the way up that does not track the curve on the way back down. So that's referred to as hysteresis. Very simple systems can show this. This is some older work in my group, a simulation, just a simple alkane in a slit pore. And this is an important phenomenon in adsorption science and characterization of porous materials. And it's often associated with this sort of capillary condensation, where the amount really jumps up very sharply on the isotherm. And the picture that I want you to have in your minds is to think about the free energy of the system as a function of the loading or the nothing. So there are two wells to minimize the free energy. And at low pressure, one of these might have the lower free energy. So you're in that state, and as you change the pressure, the depths of these wells change, and at some point they're equal. And then as you keep changing the pressure, this one now is lower free energy, and you should be over here, but you're stuck in the one you started in because there's a barrier. And eventually that barrier becomes low enough and you jump up. So adsorption hysteresis is important in some applications. For example, in atmospheric water harvesting, you'd like to avoid hysteresis because you want to be able to get the water back out. And it also is sort of a complication in adsorption cooling. So I'm going to take a little detour and explain how we simulate these sorts of things. So my group does molecular simulation. So we want to be able to simulate these adsorption isotherms. So the idea is that we know that temperature and pressure and composition of the fluid outside of the MOF, and we want to predict what goes in. And so we need a model, and I'll describe that on the next slide. We feed all of that into large-scale computer simulations based on statistical mechanics. And in particular, we're often using a technique called grand canonical Monte Carlo, which I'll explain briefly. And what we get out are adsorption isotherms, enthalpies or heats of adsorption. We can simulate mixtures and get the selectivity, and hopefully we get a lot of molecular level information on what's happening inside the course. So the model's really important, and we're using very simple models. So in most of what I'm going to talk about, we're going to assume that these MOF atoms are fixed at their crystallographic coordinates. MOFs are crystalline, so you can get the structures from X-ray diffraction. And on each of these atoms, we'll place a Lennard-Jones site. And we've taken the Lennard-Jones parameters just from generic force fields in the literature that were not developed for MOFs. They were, in fact, developed before MOFs existed. And we'll sort of see how well that works, how well we can push that. And we often put partial charges on the framework atoms, and we get those from quantum mechanical calculations. Similarly, for a guest molecule like CO2 or water, it's again a simple Lennard-Jones plus Coulomb potential. We found that taking parameters from force fields developed by other groups that match the bulk vapor liquid equilibria is a good strategy. So we like these trap force fields from the Zietmans group, and we're just using simple tip 4P water. Okay, so given the model, how do we get the isotherm? So let's back up. It's a phase equilibrium problem. So you have a fluid phase in equilibrium with an adsorbed phase. And you could imagine simulating both and letting molecules move back and forth. But typically we don't do that. We take advantage of what we know from thermodynamics. We know that at equilibrium, these two phases have to have the same temperature, the same pressure, and for every species I, the chemical potential has to be the same in the two phases. Or equivalently, you could say that the fugacity are equal to the two phases. So we're going to take advantage of that and only simulate the adsorbed phase and fix the chemical potential. So we use the usual periodic boundary conditions. So there's no interface with the gas phase. We just simulate the adsorbed phase. And as I said, we fix mu, v, and t. And from the chemical potential, you can relate that to the pressure through an equation of state for the bulk fluid. Since the chemical potential is fixed, the number of molecules in the system will fluctuate. And in fact, the key thing we want to calculate is the average number of molecules in the system. So we have different types of moves. And if you know a little bit about Monte Carlo, you've probably seen translation moves. You pick a random molecule, perturb its position, you calculate the change in energy that would occur, and you accept or reject it with this Boltzmann weight. So we do those types of moves. But we also need moves that allow the number of particles to change. So we have insertion moves, where you pick a random spot in the box, you attempt to put a new molecule there, you again calculate the change in energy that would occur, and accept or reject it with this criterion, which now includes the fugacity, the current number of molecules in the system, as well as the the change in energy. And so you can imagine, if you stick a new molecule in there and it overlaps with existing molecules, this will be some very large positive number, and this exponential will be basically zero. Those kind of unphysical moves will be rejected. And then similarly, there's a deletion move. So we do millions of these moves and average over the configurations to calculate the things we're interested in. So we're not explicitly simulating the reservoir. It's just represented by the chemical potential. We're just simulating the molecules inside the molecule. And so that gives us 1 point on the adsorption isotope. And we've developed codes in my group for doing this. The original music code is now over 20 years old, but we have a newer code, RASPA. And in fact, if you're interested, there's a newer version that just came out last year. And then with people at Argonne, we developed a version of this that runs on GPUs. It's super fast. And these are all open source, publicly available. So yeah, this is what we want to calculate. The isotherms. This was the first paper from my group on MOFs. This is back in 2004. It's actually with Omar Yagi, one of the people that won the Nobel Prize today. So his group had measured these adsorption isotherms, and we simulated them. And this was really a prediction. So we're not adjusting the parameters to match the data. Okay, methane's a pretty simple system, but over the years, even these very complicated shapes in these CO2 isotherms, these fairly simple models work, I would say, surprisingly well. Now, there are limitations, and we can get into that. So how do we simulate hysteresis? Basically, we just simulate sequentially. So you run the simulation at one pressure or fugacity. You get to the end, you save the final configuration, and you use that as the initial configuration for the next pressure. And you work your way up the isotherm blue, and you work your way back down the isotherm in orange. And in some cases like this, they don't trace. You see this hysteresis. Turns out there's another way you could do this. So instead of fixing the chemical potential, you could fix the number of particles and calculate the chemical potential. A method called Witten insertions. You run an NVT simulation, and periodically you just throw in, we call them ghost molecules. Each of the ghosts, you calculate the energy that it would feel, but you don't actually leave it there. It's just sort of a probe. And you calculate this ensemble average, and that gives you the chemical potential. And in fact, I used this in my very first paper as a PhD student. So we have two complementary methods. In GCMC, we fix the chemical potential or fugacity and calculate the loading. With the Witten insertions, we fix the loading and calculate the fugacity or the chemical potential. So we tried both of these. And this was work done by Zhao Li, PhD student in my group. And this was a hypothetical MOF in a database of MOFs we had made. The key thing to note here is that it has a fairly big micropore, about 18 angstroms in diameter, and a mesopore that's about 28 angstroms in diameter. Here's the force field. It's pretty much what I described earlier. And yeah, so I showed you the results from the GCMC. So then we ran the Witten insertions. We get the curve in red. So what are we looking at here? If we think about the blue curve, so this black dotted line, that's where the free energy here and here are the same. So, if this were like in perfect equilibrium, you would expect the isotherm to jump up here. But what happens is you get out here into this metastable region in the GCMC simulations. It gets stuck at these low loadings, and then eventually it jumps up here. The red curve, again, we trace out these metastable states, but they go on out here to a spinodal, or a point of, the limiting stability here. And then these points in between are thermodynamically unstable states. You'll never see them in GCMC or in an experiment. But since we're fixing the loading, in these Whittam insertions, we can go ahead and do simulations at those points. And then similarly on the desorption, again, there's a metastable region and then it jumps down. And so these loops are known as van der Waals loops. If you think back to equations of state, cubic equations of state have three roots. You have this unphysical region in the middle. It's the same thing here. If you look into the simulation, what's going on down in here, we're filling the small micropores that are in the corners. When we get out to here, the mesopore is starting to fill. It's maybe less full than it looks here. And by the time we get up here, of course, the whole thing is full of molecules. And if you look closely, it looks like there might be a second van der Waals loop here. If you go to ethane, now you clearly see that there are two of these van der Waals loops. One associated with filling the micropore and one associated with filling the mesopore. The other thing we thought was interesting here is if you look at the blue curve, on the way up, there's one step, two steps, with this little plateau in between. On the way down, there's only one step. You go the whole way from filled to basically empty in one shot. And that has to do with the positions of these spin notables. And one of the reasons we thought this was interesting is there's an IUPAC classification of hysteresis loops. And what we're seeing doesn't fit in any of these. So sort of fundamentally interesting. Now the material I showed you was a hypothetical MOF. And we thought about, oh, it'd be nice to sort of see this experimentally. So we need to find a real MOF. So we looked at this DNU T60, which again has pores that are about the same size as the one we were looking at before. And again, it shows two steps on the adsorption in blue and one step on the desorption in orange. And I'm hoping that some of my experimental collaborators can confirm this experimentally. If you change the temperature, these loops sort of wash out as you would expect. There's sort of a critical temperature above which you don't see this behavior. We can do bigger molecules. We did hexane, and here's maybe an opportunity for me to comment on these error bars. We see big error bars on these Whittam insertions. It's the same problem we have with the insertions in the GCMC. You're shooting in a lot of particles that land on top of the framework or other molecules, and they're not really helping your averages. But if you run this long enough, you can trace out these curves. It's known from bulk systems that simulating these van der Waals loops, you see system size effects. You make your simulation bigger and it's change a little. So we wanted to check that here and see what would happen. So everything I showed you was done with one unit cell, and one unit cell has one mesopore and one micropore. So what happens if we go to 2 or 4 unit cells? So here are the results. And let's just focus on the upper loop. So if we have one unit cell, we have one van der Waals loop. If you have 2 unit cells, you have 2, 4, and if you count carefully, there are 8 here. So let's look at this one more carefully. What's happening is each of these is associated with filling one of the mesopores. So here, they're all open. You go through that loop, you fill one of them, you fill the second one, and so on. Maybe a practical point for maybe some people in the audience, there's an empirical equation that's used to predict the minimum pore size below which adsorption, desorption should not show hysteresis. And it's empirical. And so we were interested in kind of testing this. So we ran argon isotherms in a large number of structures, and we actually find quite a few that display hysteresis below this diameter that's predicted by this equation. So this is something that you might use with a bit of caution. So how are these results related to experiments? There are clear differences between what I'm doing in these simulations and what people do in an experiment. Remember, in an experiment, molecules obviously have to move from one phase into the other. In these simulations, I'm just shooting them in here randomly. I'm not worrying about how they got there. Some people have looked at how the molecules get in there. There's nice work from Lev Sarkisov and Peter Monson where they actually set up an adsorbed phase and a fluid phase and watch the molecules move back and forth. But it's interesting that we still see this hysteresis in these GCMC simulations. And I think one way to think about it is sort of a time scale. Of course, there's no time scale in Monte Carlo, but this picture still applies. You know, what happens in an experiment is you get stuck in one of these states, and there's a free energy barrier to get over to the other one. We have the same thing in our simulations. We're in one state, and we're doing the simulation by putting in like one particle at a time, taking out one particle at a time. And so these moves, there's something fundamental that sort of mimics what's going on in the experiment. And it brings up an interesting question of what does it even mean for a simulation to be equilibrated in a metastable state? I remember when I was a graduate student reading a paper where they made the very sensible claim that if you saw hysteresis in your GCMC simulations, you basically had an equilibrator. And in some sense, I can't argue with that. But you know, what we see is fairly reproducible. Similarly, in experiments, you might argue, oh, if I just waited long enough. So I've talked to a colleague who said he tried this at one point. And I think the problem is, if you start thinking about the time scale to get over that barrier, like, okay, waiting a day or a week is not enough. You're talking about like waiting a century. So I think there are these interesting fundamental questions about how these simulations are related to what's going on in experiments. But I'll shift gears and start talking about simulations of water. So one of the motivations for looking at water is this idea of atmospheric water harvesting. Could you harvest drinkable water out of the air? If you do the back of the envelope calculation, there's a lot of water in the air. It's distributed around the whole world. And so people have been looking at sorbent-based water harvesting. Other people do like dew harvesting, but that only works at really high relative humidity. And you might want to do this in very dry locations. So we had a project from Dartmouth, and they wanted something that might sit on the back of a Jeep, or something that would be like the size of a canteen. You could put it in your backpack, and then it would give you, in our case, we were going after the canteen. They wanted 5 liters of water out of the air per day, even at like 10% relative humidity. It's Dartmouth. They want hard problems. So we were part of a team looking at this. So Omar Farha and I at Northwestern were focused on the materials. What do you put in this device that would capture water under these very dry conditions? Honeywell was involved in designing and building the prototype system. Fascinating chemical engineering, lots of good heat mass transfer. And then NewMat is a startup company that was sort of the interface. How do we take these micron-sized crystals and interface them into the device? So we have a paper came out recently, describes the whole team effort. And I'll focus on the materials part. So, MOFs are interesting for this. We can change the hydrophobicity or hydrophilicity by changing the pore size and geometry independently of changing the surface chemistry. So we took a two-pronged attack. We had a hypothesis-driven thrust, and we did some high-throughput computational screening. And I'll mostly talk about the hypothesis-driven work. So the hypothesis came from my collaborator, Omar Farha. And for water harvesting, you need exceptionally stable envelopes. You need to fill and empty them multiple times per day for this military application. And there's high surface tension, and that surface tension can basically collapse the MOF. So you need very stable MOFs. And it was known that phosphonate-based MOFs were exceptionally water stable, but they hadn't really been looked at very much for this application. So that was our hypothesis. Let's look at phosphonate-based MOFs. So we started with two known ones from Paul Wright's group at St. Andrews. So those are shown here, STA12 and STA16. They can be made with a variety of metals, but I'll focus on these two. They have one-dimensional hexagonal channels, pore size about 9 angstroms or 18 angstroms. And the metal nodes are here. They kind of go into the screen and form this helical chain. Each metal node is a single atom. It's connected to a nitrogen and then 4 oxygens that come from 2 different linkers. And then the 6th coordination site here is occupied by a water molecule. And the modeling was done by Faramars Judaki, who was a postdoc in my group. So here are the experimental isotherms in these MOFs at a variety of temperatures. The top shows the isotherms on a linear scale and a log scale. And we were pretty excited by this. The STA16 shows quite high uptake of water, about 0.8 grams of water per gram of MOF, which is high compared to other things in the literature. And the STA12, it's lower, but our team really got focused on this 10% relative humidity target. There were other targets, but we were really focused on this one. And this is one of the best things in the literature, if not the best, at this low relative humidity. So yeah, my group was going to model this then and see if we could do even better. So this is one of the places where these very simple models that I described start to break down. So we know these simple models don't do a good job in describing the energetics of a water molecule bound to one of these metal sites. So we started with some DFT calculations. We brought in a water molecule in purple here, tried lots of different locations and found the lowest energy site, and it is indeed bound to that metal. It forms a hydrogen bond with this neighboring PO group. If you try the same thing with the force field, the lowest energy site is not at the metal, it's just hydrogen bond here. What if you bring in the second water? So here's the first one. We brought in the second one. It basically hydrogen bonds with the first water and this other PO group here. So since the force field doesn't do a good job at this, and DARPA didn't want to fund a fundamental project on modeling that interaction. They want answers quick. So what we decided to do is we just fixed this water on the metal and basically considered it part of the framework. And then we modeled the adsorption of the additional water molecules. So here are the results. So the simulated isotherm starts here. It doesn't start at 0 because we have some waters already on the metal. And yeah, we get nice agreement with the experiments. One maybe detail for the simulation people in the audience, the value for P naught here. What we do for the experiments, obviously, is use the experimental vapor pressure. For the simulations, what we think the best, the most consistent thing to do is to use the vapor pressure of your model. So we're using the vapor pressure of tip 4P water here to get this curve. And if you look at what's going on down here at low loading, the new water molecules start to absorb near these hydrophilic sites. You get sort of a monolayer of water by the time you get out to here, and then the pores fill up with water, as you might expect. We can look at this, some other features. We can look at the energies. So experimentally, they measured it's the enthalpy of adsorption, but in this field, they call it the heat of adsorption. So QST. So the experiments are in blue. Our simulations agree really, really nicely. And from the modeling, you can break up that energy. Here's the total, but you can break it up into the water loss interaction and the water-water. So, you know, as you would expect at low loading, the water molecules go to the most favorable sites. They have pretty strong adsorption. Out here, this is really weak adsorption. You know, it's like 10 or 15 digits per mole, but it's made up for by the attractive water number. You can look at the hydrogen bonding. So at low loading, most of the water molecules form one hydrogen bond, and that's with the framework. But as you increase the loading, you start to see waters forming more hydrogen bonds. And out here on the isotherm, the average number of hydrogen bonds per water molecule is 2.79, which is very similar to the value of water. I mentioned high throughput computational screening. And my group spent a lot of time on this. I could have given a whole other talk on computational screening. You know, the basic idea is start with some large number of structures, run the simulations, narrow down to your candidates, talk to your experimental friends, and hopefully solve the problem. And we've developed a lot of tools to make this possible. Here, though, and so here, you know, we've done this for like hydrogen and methane, where you can simulate, you know, 100,000 materials. For water, simulating each of these points took a few weeks. So we're not going to do hundreds of thousands of materials. Now, we ran these points in parallel, so, you know, that sped things up. But we kind of gave up hope on simulating full isotherms for a large number of materials. So instead, oh yeah, okay, why is this so hard? Well, it goes back to how these simulations are done. We're inserting these molecules randomly, and you know that's true for methane as well. But for water, you also need to worry about the orientation. And actually, we can bias that, and we can solve that problem too. I think the problem with water is you have these sort of concerted behavior. You know, one water moves, well, then they all have to sort of adjust to get the hydrogen bond to rearrange. And so it's just incredibly time consuming to run these simulations. So what we did is we only ran the simulations at 10% relative humidity. And even here, I cannot guarantee that these are all equilibrated. But we did identify some interesting materials that have high uptake of water at 10% relative humidity. But let me sort of keep talking about this thought of these simulations being so hard. So, you know, I showed you two complementary methods. They both suffer from the same problem. There are other methods. There's this gauge cell method from Alex Nymark. I'm not going to talk about that. There's also something called transition matrix Monte Carlo, which turns out to be a nice solution for this problem. And I won't talk about it in detail, but just briefly, it's a flat histogram method. It allows you to calculate energy barriers separating the equilibrium phases. And if you're interested, these are really the folks who have developed this, and you should take a look at their work. We have implemented this in our GRASPA code. So the idea is you run the simulation, the TMMC simulation, at a single fugacity, and you can predict the probability of observing all of these different loadings at that fugacity. So you can get a probability curve. And that probability is related to a free energy. And so you can see, for example, here you have, you know, two minima, and so you can figure out, is this the low energy minimum, or is this? But the real beauty of this, though, is that there's an analytical formula that allows you to take the results at one fugacity and map them onto any other fugacity. So if I have the black curve, I can get the red curve and the blue curve for free. So you can get these free energy landscapes. So you can trace out the van der Waals loop, you get the spinodals, you can get the binodal, where the free energies are equal here and here. And because of this analytical reweighting formula, it gives you continuous isotherms. So in the results I'm going to show you, the isotherms will be lines as opposed to discrete points. So, yeah, so we decided to look at water in this particular moth, NU1000. And this was done by Philip Malik, who's a research professor. So the first thing we did is we went out and found all of the experimental isotherms we could. They're plotted here. These are the full isotherms. And here we're zoomed in on this low loading portion down here. And what do you see? Well, at low relative humidity, there's quite a spread. At high load, there's quite a spread. The pressure where the condensation step varies, the width of the hysteresis fluid varies. So there's quite a lot of variation. And in looking back at this literature, what we realized is, fields progress. So when some of these measurements were done, people didn't think about what these nodes looked like. So this is the zirconium node in these moths. And you have some places where these carboxylates from the linkers come in. But in this particular moth, you also have spots here where there's no linker. And you could have what they call a modulator, like something like acetate. Or you could have an OH and a water, something that has a plus or a -1 net charge. And in some of the early measurements, people didn't pay attention to, well, how did we pre-treat them off? What solvent did we make it in? So they didn't know how these nodes were terminated. But the most recent isotherm, the field had become aware of all this, and so they paid attention and documented it. And so they think that their material has these OH and water terminations on the node. And so we decided, okay, we'll take their isotherm and we will make our nodes look like that. If we look at this in a little more detail, so here's a terminal OH, here's a terminal water. There are also these bridging OHs and bridging oxos. So there are a fair number of hydrophilic sites on these nodes where water might nucleate. So this was our prediction. It's not that good. We thought we could do better. So we did some DFT calculations. So if we zoom in on the node, we brought in a lab molecule. And here, this is more of a schematic, but it's easier to see what's going on. So we brought in water, minimized, found different locations. And one of these modes, the adsorbed water, forms a hydrogen bond with the bound water and a hydrogen bond with this bridging oxo. There's another mode, it's pretty similar. Oh, the other thing I should point out in this mode, the bound water and the OH form a hydrogen bond with each other. So there's this intranode hydrogen bond, because they can rotate. In the third mode, that intranode hydrogen bond is broken, but the new water can then form 3 hydrogen bonds with the framework. So we're going to hold this all fixed. So we had to pick what configuration that we use. So we started with the configuration where there's this intranode hydrogen bond. And that's the result I showed you earlier. I'm going to color code that green. What if we break that hydrogen bond? We rotate the water in the OH. That helps a little. And we do start to get a little bit of water at low loading. The blue is higher than the green here. What if we bring in one more water and just fix it too? That makes things even worse. And then we thought, well, experimentally, if you heat the moth high enough, you can remove that bound water. So what if we just take it off and let the simulation decide, okay, we're going to put a water there or not, and what orientation does it want? And I said earlier that the force fields are not great at capturing the interactions with these metals, but for zirconium, the force field turns out to not be too bad. And so this works pretty well. We get this adsorption of water, before the step, and we get the step in nice agreement with the experiments. And it's sort of a computational trick, but I think the key thing is it allows the water to adjust to incoming water molecules. So we're capturing that flexibility in kind of a simple way. We can look at the radial distribution functions between the absorbed water and the framework. In the green system, the water molecules don't really like the framework. They like each other, so they cluster. So most of the water in the system, they're all here together. In the black system, now you have lots of interactions with the framework. And so the water's more spread out over the surface. And so, holding that bound water in that OH rigid introduces an artificial hydrophobicity. And that could have a big effect on the adsorption isotope. You saw how far that shifted. And MOFs are known, certain classes of MOFs are known to be flexible. They could exhibit breathing, big motions in pore size, or gate opening. So this sort of classic flexibility. But I think what this study shows is even local flexibility of these ligands on the node can play a big role. So even what you might think of as rigid MOFs have some flexibility that can be important for some applications. Okay, so that brings me to the end. I've tried to show you some of what we're doing in the area of adsorption hysteresis, trying to gain some insights into that, and talked a little bit about what we're doing simulating water, try to give you some idea of why is this so hard. And in terms of going forward, this TMMC method, I wish we had started doing it 5 years earlier. I think it's really useful. Like many groups, we're starting to use these machine learning interatomic potentials, improve sampling, that's sort of related to the TMMC, and GPU computing is helping quite a bit. So the work that I did, I think I acknowledged the people in blue as I went along. And again, thank you very much for the invitation. I was really honored, and I'm looking forward to the rest of my day, and I'd be happy to take questions.